Last version of section 1.3 from the OpenStax PreCalculus book. A few topics you're learning here. The main one, I would say, is being able to calculate the average rate of change, which sounds a hell of a lot worse than it is. In fact, I bet you already know how to do this. If you know how to calculate the slope of a line, which I'm guessing you do, maybe recall this whole y equals mx plus b thing that was probably drilled into your head at some point, where the m in this equation is the slope, and you can calculate the slope as the rise divided by the run. And if that means nothing to you, you can calculate it as the change in the y coordinates over the change in the x coordinates, which sometimes is written delta y over delta x. Anyways, if you can do that, which I'll work out an example real quick, you can do everything you need with the average rate of change. That's all you're going to be doing in this section. So let's see, if I were to calculate the slope of this line right here, well, I'd need two different points. Here's one of them, here's another one. I could think about it as rise over run, rise being how far I go up, and run being how far I go to the right. So it looks like I go up by, what, -3. 1, 2, 3. I'm going down 3, so I'm going up -3. And then run, how much I go right, well, let's see, 1, 2, 3, 4, 5. It appears that the slope, the rise over run, is -3/5. And I think that's true. You could, if you wanted something more of an equation, more of a formula, you could arbitrarily call these points, maybe this one x1, y1, and this x2, y2. Note, you'd get the exact same answer if you called this x1, y1, and this x2, y2. But at any rate, whatever you call them, you plug it into this formula. You say what? y2 is -2, y1 is 1, x2 is 3, x1 is -2. And sure enough, -2 minus 1 is -3, whereas 3 minus -2 is 5. So you end up with the exact same answer right here. You're like, well, what's that got to do with average rate of change? Turns out that's exactly average rate of change. For average rate of change, you're not given this line in blue right here. You're instead given some function. Doesn't matter what the function is. There's a really messed up looking function. Something like this. Maybe I call it f. It's function in red right here. And you're told 2 points. So maybe I ask you to find the average rate of change of this function f on the interval from -2 to +3. Oh, that looks very different than this question up here. Turns out it's the exact same question. All this is giving you when it gives you the interval is the 2 x coordinates. That's it. And so you look at this graph in red right here, and you figure out the 2 y coordinates. And if you have the 2 x coordinates and the 2 y coordinates, you can figure out the slope of the line between those 2 points. The slope of the line between those 2 points is exactly the average rate of change. Often you'll see the formula written a little bit differently. It'll say average rate of change is f of x2 minus f of x1 divided by x2 minus x1. But note, this is exactly this, right? F of x2 is just saying the output from the function f when you put x2 into it. That's just y2. You graph on the y-axis the outputs of the function. This is the same as this. But this notation is a little bit easier to use when you're trying to figure out the average rate of change. So imagine we're starting over and all we have is the stuff in red. That's all you got. And it says find the average rate of change of f on -2, 3. What you have to know is these are your 2 x coordinates. So you can arbitrarily name them x1 and x2. So if I call x2 3, and x1 -2, then in the denominator here, I'd have 3 minus -2. I already got half my formula done. Right? Average rate of change is just this fraction right here. I already got the bottom done. All I got to do is figure out the top. If x2 is 3, what is f of x2? It's just the output from the machine when you put x2 into it. What comes out when you put 3 into it? Well, that's easy. You just come over here to 3 and figure out what height corresponds with an x coordinate of 3. And it looks like that's -2. So I'd look at my graph right here, and I figure out that the height when x equals 3 is -2. So instead of f of x2, I can write -2. Similarly, to figure out f of x1, just be like, that's what comes out of the machine when you put x1 into it. x1 is -2. -2 is right here. The height is +1. So I got -2 minus 1. And if you go through and do this math, you'll get this familiar fraction of -3/5. That's average rate of change. That's it. There's another way you can, okay, so the way these questions will be asked, anytime you have a function, you can figure out the average rate of change. You'll always be given the 2 x coordinates. All you got to do is be able to figure out the 2 y coordinates. So whether you figure out those y coordinates from the graph or figure them out from an equation, like something, I don't know, g of x equals x squared minus 1, and I ask you to find the average rate of change on the interval -3 to +4. Fine. You do that? I mean, I could work through it, but this is the fast version of the summary, so I'm not even going to do it. This is x1, this is x2. You can figure out y1 and y2 by taking these and putting them into the function. y1 would be 8, y2 would be 15. Plug all those into a fraction, and you'll get figure out what your average rate of change is for this function on this interval. That's it. That's one of the 3 topics. The other 2 are things that are a lot easier than the definitions of the book might make them seem. As I kind of ranted on and got off on a bit of a tangent in an earlier video, you can make these a lot more complicated if you get really technical on the definitions. And it's good to understand how the technicalities of those definitions correspond to your intuitive understanding of these concepts. For the sake of this quick video, I'm just going to understand the concepts. And then if you really want to understand, if you're an A student, if you're really trying to get everything you can out of this class, maybe understand how this intuitive understanding that I'm going to supply you with matches up with the book's definitions of increasing, decreasing, and the different values of extrema. Increasing. A function's increasing when it's going up. That's it, when it's going up. What do you mean by going up? Like going straight up? No, like pretend you're hiking and you start out over here on the far left and you're trying to get to the far right. Anywhere you're going uphill, the function's increasing. Right? If I didn't give you any definitions, just ask you to figure it out yourself, you'd probably guess that the function's increasing here, decreasing here, increasing here, and decreasing here, and you'd be exactly right. It's increasing on all the green intervals, it's decreasing on all the red intervals. It's increasing from -4 to -3. Note I'm specifying the x coordinates there. And again from -2 to +1. And it's decreasing from -3 to -2, and again from 1 to 4. That's increasing and decreasing. Extrema. Extrema come in a couple different flavors. There's local extrema. Extrema are minimums and maximums. And there's absolute, aka global extrema, minimums and maximums. Absolute minimum and maximum. The absolute minimum is the lowest point on the graph. Right here. Lowest the graph ever gets. Absolute min. Right there. Absolute max is just the highest the graph ever gets. That guy right there. That's it. Local min max. They're like, well, this point right here seems special, right? It's kind of this hilltop idea. But it's not the absolute maximum because this point's a hell of a lot higher than this point, but this should still get some sort of a name, shouldn't it? Yeah, it should. It's this local max. A local max is just any point that's higher than all of its immediate neighbors. There's a local max. This point right here, you might guess would be a local min. Guy right there. And so there's one other blue point, this guy right here. It's got to be something, right? It's not the absolute minimum, because this point's way lower than this guy. And you're like, oh, it's a local minimum, right? Actually, it's not. For reasons I'm not going to get into on this video, endpoints never qualify as local minimums or maximums. So this point wouldn't get anything special. It's just an endpoint. Different books define that a little bit differently. Your book just kind of avoids the subject and doesn't give you endpoints like this. It usually gives you arrows instead of endpoints. You don't have to worry about those points. But just an FYI, when you're trying to find local minimums and local maximums, endpoints don't count. If you're trying to find absolute minimums and maximums, endpoints absolutely could count, but not for local ones. That's it. Actually, one more thing I want to say. It's possible that a graph doesn't have an absolute minimum. Imagine that this is an arrow going down, goes down forever. Then there is no absolute minimum. You'd still have a local minimum right here, but it wouldn't have an absolute minimum. That's it. That's all the concepts from 1.3, so I'll stop the quick video here.